So today we are going to do some calculations concepts, especially we are going to start at the bottom of vacuum distillation column. So first let us look about the diagram of the vacuum bottom sections. So feed, that is from the atmospheric residue, is first sent into the furnace where the feed has to be preheated, and after leaving the furnace at a heated feed is charged into the bottom section of the vacuum distillation column. So this is about the feed. Then you can see there is a one portion that is air leakage, and that is denoted by A. This is a new term that is being introduced here in the vacuum. We'll discuss it in the next slide. Then at the bottom there is a steam. We'll already have discussed about the importance of steam in the bottom of distillation column. This is the bottom products leaving from the bottom section, almost a very much short residue from the distillation column. And then the material that is leaving from the bottom section, that is from the flash zone, is basically VAOFZ, that is a vapor leaving from the outlet of flash zone, is total D. Total D means total D is total distillate products. L0, as we know about, L0 is about the overflash, and there is one new term G, and there is a one term A. So A is basically for the air leakage and SW is for the steam. So we'll discuss these two new terms that has been introduced here, A and G. We'll discuss in the next slide. So this is all about the streams that is going inside into the bottom of the vacuum distillation and leaving the vacuum distillation. So now come to the assumptions part, which describe about the air leakage and decomposition gas, G. So for that thing, so we have to go for the assumptions because it is operated at a very high temperature. So that's why there are some assumptions behind, there are logics behind the assumptions. So the first assumption is amount of hydrocarbon decomposition gases. What it means that these hydrocarbon gases are produced in the process by virtue of the high temperature to which the reduced crude is subject. Due to such a high temperature, there are crackings and there are the chances of forming the decomposition gases. The symbol G is basically used for the decomposition gases in the material balance calculations. Now come to the second one, that is the A, symbol A value for the inward air leakage. We know that in this distillation column is a vacuum. So inside the column there is a vacuum, but outside there is atmospheric pressure. So obviously there are chances of the air flow inside the column. So we have assumed that any air that is flowing inside the column due to the leakage and some other reasons, that all the air are basically injected are going inside the column at the flash zone level, and that can be the symbol can be taken as A. So for the heat balance, this leakage is assumed to occur totally at flash zone, and the symbol A is used for the material balance. So this is all about the two new things that has been introduced in the bottom section: hydrocarbon decomposition gases because of high temperature subjected for the reduced crude, or the second thing is the inward air leakage. Now come to the overflash, about the overflash. So we know about the overflash. So overflash is depending on the degree of purity of HVGO, heavy vacuum gas oil. So this all about depend on this issue, and normally it is taken at 1 to 2 volume percent of the feed of the vacuum tower, as in the same we have taken 1 to 2 volume percent in the atmospheric column. So assume for all calculations 2 volume percent of atmospheric residue. So overflash is taken as a side stream. This is a new thing for the overflash. It is taken as a side drop product, and sometimes it is also called as a slope oil. So if we are taking this as a product, this is called as a slope oil. So this is all about the overflash. Now come to the flash zone pressure. So there are a very common method for calculations of the flash zone pressure or any pressure. So for that thing, first we have to know about the different trays and internals available in the various section of the tower for the pressure drop calculations. The second thing, the number of trays between the loop tower is normally 3 to 5 between the two draw trays. So and modern fuel towers, they normally uses the grid sections in between the draw tray. So we can have, if we have know about these informations, we can calculate the pressure drop using this recommended table. So these are the basically recommended values for the fuel type. You can take 6 to 8 mm Hg pressure drop. For the lube type, you can take 1 to 2 mm Hg pressure drop. And if there are chimney trays, and for the grid section, you can take 1 to 2 mm Hg. For the fractionating trays, you can take a 2 to 5 mm Hg pressure drop. So these are the basically pressure drop recommendation values can be vary, but these are the recommended values for the calculation of pressure drop at the flash zone. Now come to the next step, that is the bottom steam requirement at the flash zone, because we have also the steam at the bottom section. So how we can calculate, that is a very simple calculations is required here. So the first thing that you should know, the number of total moles at the flash zone, that is steam, hydrocarbons, air leakage, all these are in the vapor phase in the flash zone. So total number of moles, so moles of total hydrocarbon, moles of steam at the flash zone, and moles of air leakage. So we can write D, SW and A. This is all number of moles. And if we want to find out the hydrocarbon mole fractions, so we know about these are the basic calculations. Moles of hydrocarbon divided by the total moles, that is YHC, can be calculated as D upon total moles. So this is a formula. If you rearrange here, SW is our basically, this is the important thing, SW is the steam requirements. So rearrange all these equation and you can find out the SW is nothing but D upon Y, that is the mole fraction of hydrocarbon, minus D plus A. So this is all about the steam calculations, where SW is the amount of steam in the moles, D is the total hydrocarbon distillates, YHC is the ratio of hydrocarbons, and A is the air leakage. We can calculate all these things with the help of all these input values. We can find out the steam requirements. So this is all about in the bottom sections. For that, after that we can go for the material balance procedure. For the material balance procedure, we have to know these things. For example, we should know for a flash, we have to know amount of hydrocarbon decomposition gases. We should know about the air leakage, and we can assume that value also. And the maximum flash zone temperature, that has also should be known. For example, in our case, we can take the maximum temperature up to the 800 degree Fahrenheit. We can also find the top pressure. So these are the informations that we need to know before going for the material balance. So this is all about for today's lecture. We'll discuss some calculations in the next lecture. Thank you very much.